Hi everyone. Today we're going to be looking at thermodynamics and equilibrium. Now, our syllabus outcome is examine how activation energy and heat of reaction affect the position of equilibrium. Just as a bit of revision on last lesson, just remember that collision theory is the driver of Le Chatelier's principle. An increase in collisions causes an increase in reaction rate. Unbalanced reaction rates need to balance to restore equilibrium, and reaction rates will balance out after a system is disturbed. Now, on to today's stuff. So thermodynamics and equilibrium. We know by now, hopefully, that the reversibility of a reaction depends on thermodynamic factors, mainly enthalpy, entropy, and Gibbs free energy. But how do these factors affect the position of the equilibrium? So what we mean by position is, is it going to be mostly products? Is it mostly going to be mostly reactants? Is it going to be a nice even mix of both? So let's have a look at the thermodynamic factors that will affect it. So firstly, enthalpy. So our exothermic reactions happen much more readily than endothermic reactions, just because for an exothermic reaction, you've got a little hump to get over, so a little bit of activation energy and releasing a lot of energy. To get back over the hump, you need to add in a lot more activation energy to get back. Okay, and so therefore the exothermic ones happen much more readily. In an equilibrium system, if the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. And so we can have a thing, if the forward reaction has to get up to the certain activation energy and then drops right down, it's going to be easier to occur that direction rather than the opposite direction where the products need a whole heap of that activation energy to get back up over the hump to get back to the reactants. So all things being equal, exothermic reactions will occur faster than the endothermic reactions, and again that comes back to the definition of a reaction. A rate of reaction is dependent on number of successful collisions with enough energy. And so, you know, if you require more energy for the reaction to occur, then the reaction will go slower. So all things being equal, the exothermic reactions will be faster than the endothermic reactions. If the forward reaction is exothermic, then the equilibrium will lie more to the side of the products. Okay. And the converse is true. If it's endothermic, it will lie more towards the side of the reactants. The degree of preference for reactants or products is dictated by how endo-exothermic a reaction is. Something huge like combustion, we know that that's pretty much one way, okay? Just because it is so exothermic, the reaction literally can't get back up the hill to go do the reverse. But something where it's nice and even, it'll happen much more evenly. So as our delta H approaches zero, the equilibrium has more equal concentrations of reactants and products. The larger the delta H in either direction causes that imbalance. Now with entropy, so remember entropy is our measure of disorder within a system. Typically reactions that increase in entropy occur faster, and that's because with the natural state of things, the universe likes to go towards a state of increasing entropy, increasing disorder. If the entropy of an equilibrium reaction increases in the forward reaction, this reaction will occur faster, and so it'll favor the product side. With Gibbs free energy, our spontaneous reactions occur much more easily and faster than non-spontaneous reactions. If we think about delta G, when delta G is equal to zero, the forward and reverse reactions have the same spontaneity, so happen at about equal rates. Again, all other things being equal. So this means that the position of the equilibrium would be quite even. If we have a system that is between -30 and 0 kilojoules per mole for our delta G, the forward reaction occurs faster than the reverse reaction. Okay, so remember, in an equilibrium system, for delta G, our forward reaction is equal but opposite to our reverse reaction. And so if our forward reaction is spontaneous, our reverse reaction is non-spontaneous. But we have that little window where it kind of overlaps a bit, and that's a 0 to -30. So basically what this tells us is that for that range, that negative 30 kilojoules per mole to 0 for the forward reaction, it means that there's going to be more products than reactants in the system. Okay, so it's mostly going to be products, a bit of reactants. If it's between negative 60 and negative 30, the forward reaction is much, much faster than the reverse reaction, which means that the equilibrium lies far to the product side. So we mostly products, tiny little bit of reactants. Okay, it's almost a one-way reaction until it hits that negative 60, in which case it is just a one-way reaction. The true is opposite in the reverse order. So 0 to positive 60, 0 to positive 30, it favors reactants. 30 to 60, it greatly favors the reactants, and above 60, only the reverse reaction occurs. Okay, so this is a nice little diagram showing us what we can expect based on the delta G of our equilibrium system. So if it's at 0, we can expect about even amounts of products and reactants. 0 to negative 30, it favors products. 0 to positive 30 favors reactants, so on and so forth. Now, activation energy. Increasing the activation energy of a reaction slows down the reaction rate. And again, that comes back to collision theory, saying that for a successful collision to occur, it needs to occur with the right orientation and enough energy. Now, it does this, but it does it for both the forward and reverse reactions. So if we change the activation energy, we don't actually change the position of the equilibrium. Okay. Basically, this is why catalysts, so we've mentioned that catalysts don't change the position of the equilibrium, we just get to the equilibrium faster. And that's because catalysts change the activation energy of our reaction. So it typically lowers the activation energy by providing an alternate pathway. That's how a catalyst works. But following Hess's law, delta H of several reactions will be the delta H of the overall reaction. And so what we get is that the delta H, delta S, delta G, they're all the same regardless of the activation energy. So that really determines the side that our equilibrium lies on. Whereas our catalyst, just because it just affects energy, activation energy, it doesn't affect our delta G, so it actually won't actually affect where the position of the equilibrium is. So, having said that, let's have a look at an example. So here we have this most important reaction, the Haber process. We have this thermodynamic data, so our delta H is negative 92 kilojoules per mole, and delta S is negative 199 joules per Kelvin per mole. So again, I've forgotten to put it in that per Kelvin in this lesson as well. It should be J dot K to the negative 1 dot mole to the negative 1. Now we want to determine qualitatively where the equilibrium lies at STP. Now that tells us, remember, we look for our important bits of information and important phrases, and STP is one of them. It tells us that it's at standard temperature and pressure, which is 25 degrees Celsius and 100 kilopascals. So we can use that. We figure out our delta G using our thermodynamic data. Our temperature is 298 Kelvin, which is again 25 degrees Celsius. Using delta G equals delta H minus T delta S. Formulas on our formula sheet. We get our delta G being equal to negative 27,200 joules per mole. Okay, rounding that out, it's a negative 27 kilojoules per mole. So it's in between that 0, negative 30 window. So what we can say is that that reaction, it will favor the product side of the reaction as it's between 0 and negative 30. But there will still be some reactants. So it's not completely towards one side, but we'll get mostly, okay? And the fact that it's approaching that negative 30 means that it is starting to be more and more reactants in the system, okay? So that's how we figure out those qualitative positions of equilibrium. To summarize, thermodynamics affects the position of the equilibrium. Exothermic reactions, that should say delta H is less than 0, tend to lie towards the side of the products, Spontaneous reactions, delta G is less than 0, tend to lie towards the side of the products as well. Our change in entropy, when it's positive, that tends to lie to the side of the products. Our activation energy does not affect the position of our equilibrium. Okay, so regardless of the activation energy of a system, that won't affect the position of the equilibrium, because it's mainly the difference in energy between the start and the end that causes that imbalance in products. Okay, so that's all for today. Move on to the questions, and that's it. Thank you.